स्टेट्स या गोष्टी आपण बघितलेल्या होत्या. या पॅरामीटरमध्ये पण त्याचे ड्रास्टिक फीचर्स देखील बघितले होते, जसं की इलेक्ट्रॉनिक कन्फेक्शन मध्ये आपण बघितलं होतं की 4f and 5d orbitals are very close in energy. So after lanthanum, the 4f orbital becomes decisively more stable and next incoming electron enters into 4f orbital. It is also little importance that whether these elements contain any d electrons or not. After which we have studied the stability of these elements with respect to completely empty, half-filled and completely filled electron subshells. With regard to oxidation states, the +3 oxidation state is more stable, common and principal oxidation state, that is the group valency attributed to all these elements. We have seen all these parameters yesterday. Today we are going to see the remaining parameters with regard to lanthanide elements. These parameters are the colored ions and the lanthanide contraction. I am going to show you the slide where the color of all these elements can be seen very easily. So if you see this slide, it is seen that here we have seen that +3 oxidation state is more common here. All these elements, they do display +3 valency as a principal, common and the group valency. Here it is seen that the +3 +2 oxidation state is shown by samarium, europium, thulium and ytterbium. So the +4 oxidation state is shown by only 5 members: cerium, praseodymium, neodymium, terbium and dysprosium. With regard to color, the color also varies with regard to the oxidation states. Here it is revealed that samarium atom number 62 having +2 oxidation state is red in color, while the same element in higher oxidation state, that is in +3 oxidation state, it is yellow in color. So the same element that displays two different, radically different colors in lower oxidation state and in higher oxidation state. In lower oxidation state, it shows a red color, and in higher oxidation state, that is +3, it shows yellow in color, while europium is colorless. So lanthanum, cerium, europium +2, europium +3 and lutetium +3 and ytterbium +3, these are the members which are colorless. Rest all other elements, they show one or the other color. If we proceed further for +2 oxidation state, which is shown by thulium atom number 69, thulium in +2 oxidation state is pink in color, while in higher oxidation state, thulium +3, it is somewhat yellow in color. If we look at ytterbium atom number 70, the last but one element, it is having only one color in lower oxidation state, that is a greenish yellow color, that is for +2 oxidation state ytterbium. But in higher oxidation state, it is colorless. Now, if we move further to the highest oxidation state shown by all these elements, it is seen that the cerium +3, that is common oxidation state of cerium or the lanthanides, it is colorless, but +4 oxidation state is colored, while the praseodymium in lower oxidation state, that is +3 oxidation state, atom number 59, it is yellow in color, while praseodymium in +4 oxidation state is somewhat dark yellow in color. Similarly, neodymium in +3 oxidation state is somewhat purple pinkish in color, while in higher oxidation state, that is neodymium +4, it is somewhat dark purple in color. Promethium +3 pink in color, samarium +3 just now we have discussed yellow in color, and all these elements, europium, gadolinium, terbium +3 oxidation state, those are colorless. Then dysprosium atom number 66 in +3 oxidation state is yellow in color, while dysprosium in higher oxidation state is somewhat dark yellow in color. Terbium +4 is somewhat faint brown in color, while +3 oxidation state of terbium is colorless. Now the holmium +3 is yellow, Erbium plus 3 is again pink in color. Thulium plus 3 is pink in color. So these are the elements. They show the different colors, and this color property that is attributed to the number of unpaired electrons which are present. And we have also seen that the DD transitions or the promotion or the jumping of electrons within the energy level that gives the color, which what we call as a charge transfer, which is also observed in potential for magnet also. Here, this is the next sample, the slide, where all the elements which are shown, these are the lanthanum nitrates in 6 water molecules, having 6 water molecules from left to right. These are having some faint colors. So nitrates of lanthanide containing 6 water molecules, those are also having different colors, amongst which praseodymium and neodymium, these are the elements, they are having somewhat dark color. Now, after which, if we proceed further, the next part of this F block element is a lanthanoid contraction and its consequences. We know the word contraction means simply the size decreases. This decrease in atomic dimensions of lanthanide elements is known as the lanthanide contraction. In simpler terms, we can define lanthanide contraction as the steady decrease in atomic dimensions such as atomic number, atomic size, ionic size, with the increase in atomic number is known as lanthanide contraction. This means that lanthanum is having big atomic size as compared to lutetium, the last member of this series, which is small in size. This is because as the atomic number increases, the addition of electrons takes place in the same subshell, and here we can correlate this particular property with the another term that is known as a shielding effect, or what we call as a screening effect. Shielding effect can be defined as it is the decrease in the attractive force for the nucleus on the valence electron. So if the atomic number increases, the shielding effect decreases. That means the nuclear force of attraction over the outermost electron, that gradually increases. So the number of inner electrons, those are pulled towards the nucleus, and hence there is a steady decrease in the atomic dimensions. The drastic feature of this lanthanide contraction is that as the atomic number increases, the addition of electron takes place in the same subshell, that is the 4f. As the addition of electron takes place to the same subshell, which increases the number of electrons as we move from left to right, that is from period, that is from atom number 57 to 71. The number of electrons increases, which decreases the shielding effect. That means the number of inner electrons are gradually pulled towards the nucleus, which results in the shrinkage of atomic dimensions with the increase in atomic number. So as the addition of electron takes place to the same electronic subshell, and the electrons, the number of electrons also increases, and hence the size decreases. If atomic size decreases, the consequence of this Lanthanide contraction is that if the size decreases, it is very difficult to remove the electrons from the small size ion or atom, because these electrons which are very near to the nucleus are very tightly bound, and hence in order to remove such tightly bound electron, high amount of energy is to be supplied, what we call as a ionization potential or ionization energy. So lanthanum being larger in size, more basic, where the ionization potential is very less. But as we move further up to lutetium, which is the least basic, small in size, the size of lutetium plus 3 is very small, And because the small size lutetium ion holds all the valence electrons tightly in position in its valence shell, and hence if we want to remove either of the electrons from such a small size lutetium plus 3 ion, then high amount of energy is to be supplied. That means IP value is naturally very high. So IP values goes on increasing as we move from left to right, or as the atomic number increases, IP value also increases. So with regard to this lengthen contraction, here I am having one slide which shows how there is a trend in the periodic table with regard to the shielding effect and all other properties. Here this is a periodic table. Here as we move from left to right, for example francium, then here radium atomic number 88, and after radium atomic number 89, that is for actinium. Same is, that is cesium 55, then barium 56, and after barium atom number 57 is of lanthanum. So as we move from left to right, that is in the sixth period from atom number 57 to 71, here the addition of electron takes place everywhere in the same subshell, which increases the shielding effect. That means the number of inner electrons are pulled towards the nucleus, which results in the shrinkage of atomic dimension. Another parameter is that here I have shown you that here as we move from left to right, this is true for the group. As we move from left to right, that is from lanthanum to lutetium, then here it is seen that the shielding effect decreases, and because of decrease of shielding effect, the valence electrons are pulled towards nucleus gradually, and hence size decreases. If we move down any group, that is from hydrogen to francium, all these parameters are true down when we travel down any group. That means if we travel from hydrogen to lithium or from lithium to sodium, here the hydrogen having atom number 1, lithium atom number 3, and sodium atom number 11. Here electronic configuration of hydrogen is 1s1. The outermost electronic configuration for lithium is 2s1. For sodium it is 3s1, potassium 4s1, rubidium 5s1, then 6s1 and 7s1. The drastic feature of this addition of electron, or if we go down any group, then the addition of electron takes place to the new shell of electrons, which is exactly contrast characteristic if we travel from left to right in a period. In a period, addition of electron takes place to the same shell of electron, but if we travel down any group, addition of electron takes place to the new shell. Because addition of electron takes place to the new shell, shielding effect increases, which decreases the nuclear force of attraction for the outermost or the valence electron, and hence size gradually increases if we travel down any group. So hydrogen is smallest in size and francium is biggest in size. Same is true for beryllium, is smallest in size, and as we go down any group, here up to radium, which is biggest in size, which is exactly contrast to if we travel from left to right in a period, lanthanum in a biggest in size, while lutetium is the smallest in size. So in a group, size increases, while in a period size decreases because of decrease in shielding effect. So because of this shrinkage, if we look at the consequences or the what are the effects of this lengthen contraction, which are enlisted here in this slide. Here the gradual decrease in atomic size or ionic size of lanthanides with increase in atomic number is called lanthanide contraction. Just now we have seen. Here what are the consequences? As the atomic number increases, the positive charge also increases. That means the tendency to lose electron also decreases. So lanthanum being more basic, lutetium least basic. As atomic number increase, other things decrease. That means atomic radius that decreases, ionic radius also decreases. This is on account of the decrease in screening effect. Here I am having one slide which clearly shows as the atomic number increases, how size decreases. Here the first member lanthanum, atom number 57, and here atomic radius which is measured in terms of picometers. For lanthanum it is 188 and the ionic radius for the same element is 106. For cerium, atom number 58, the atomic radius is gradual decrease, that is from 188 picometers to 182 picometers, and the ionic radius that also decreases. So here we can see the shrinkage in atomic dimensions, that is the ionic radii, that is from lanthanum to lutetium, or the atomic radius from lanthanum to lutetium. So lanthanum is biggest in size, lutetium is small in size. Same is true for ionic radius. Lanthanum ion is big in size, while lutetium ion is small in size, having radius that is 85 picometers. So here it is seen that as the atomic number increases, there is a slight decrease in atomic dimension, and this is the characteristic feature that we can separate all these elements from one another. This is also a characteristic or the pathway to separate all the lanthanide ions from one another, because we know that all the 15 members, they occur together. They have almost similar chemical properties. Because they occur together and they are having almost same chemical properties, so scientists in the early days, they have thought of that how can we separate all these members from one another. So if for a specific purpose, for example, yesterday I have given you the reference of holmium, which is used in MRI imaging, that is the MRI technique for patients. Here, if the scientists in the early days, if they require either of these elements for some research purposes, then it was rather difficult for them to separate. But because of lanthanide contraction, we can separate all these ions from one another. That is, we can separate these ions from one another. It is only because of the size difference. That is, difference in the size. That is, physical properties of all these elements are differing from one another, and because of which we can separate the ions from one another. We have seen in this regard the ion exchange method, where we have separated all these ions from one another. So while separating these ions from one another, a aqueous solution of tripositive ions that is allowed to pass down through a column, which is just like a burette, where these ions get adsorbed with regard to their size. So the ion which is big in size, that adsorbed first on the resin. Perhaps you might be knowing the resin. These are the solid beads having fibrous open permeable structure. So these resins, that is a cation resin that is used, which adsorbs the large size lanthanum ions first on the resin bed, followed by other members in the increasing order of their atomic number. So the first chance to get adsorbed is for lanthanum, and lutetium, that is adsorbed last. So this is the first step where separation, that is only adsorption, takes place. For the effective separation of all these ions from one another, a solution of ammonium citrate citric acid having the pH between 5 to 7, that is allowed to pass down through this column, and if the flow rate that is adjusted, that is 1 drop for 1 second, then these ions, they are kept in contact with the resin bed for a very long period of time, and this period where we have adjusted 1 drop for 1 second, that ensures the close or the intimate contact of lanthanide tripositive ions with the resin bed itself, and because of this, effective separation is brought about. And if we keep a reservoir or receiver at the bottom of this column, then here after adding the solution from the top of this column, different colored bands were obtained on the column itself. These colored bands are indicative of the different tripositive lanthanide ions. For every tripositive lanthanide ion, the different colors were observed on the column itself. So the lowermost color is naturally of the lutetium. So if we start the flow rate, then first of all, the colored ions, say for example, if it is pink in color, lutetium plus 3, then first pink colored solution that is received in a receiver. When the pink color vanishes, again the stopcock is closed. The vanishes, when the pink color vanishes, this indicates that lutetium is eluted out of the column. Again, ammonium citrate citric acid is added from the top of this column, and next colored ion, which is some, say for example, for ytterbium, it may be green in color. So again, the stopcock is opened, and this solution, that is green colored solution, is again received in a separate receiver. After diminishment of this green color from the column itself indicates that ytterbium is eluted out of the column. So all these members are eluted out of the column in the decreasing atomic number. So in the first step, the adsorption takes place with the increase in atomic number. That means big size lanthanum ion gets adsorbed first, but while eluting the ions from the column, the ion which is least basic or small size ion, that is the lutetium, that forms a more stable complex with ammonium citrate citric acid, and it is eluted out of the column first, followed by other members in the decreasing order of their atomic numbers. That means here the basicity gradually increases as we move from lutetium to lanthanum. So lanthanum that is eluted out of the column at very last. So this is how we can separate these ions from one another just because of the lanthanum contraction. Perhaps it is also shown in this slide also. The larger the size of cation, greater is the tendency of such hydroxide to dissociate, and stronger will be the base. That means lanthanum is more basic, lutetium is least basic. The second effect of this lanthanum contraction, that is the ionic radii of post-lanthanides. The word post-lanthanide means those elements which are present after lanthanum are known as the post-lanthanide elements. The elements which follow the lanthanides in the third transition series are known as the post-lanthanides. The ionic radii of the element which follow lanthanum are similar to that of the element of the previous period. There is a normal increase in size from scandium to yttrium to lanthanum. Here we have to give the consequence with regard to lanthanum itself. So there is a size decreases. So all these is showing, only 10 minutes are left here. We are proceeding further with the actinide. Again, if we look at the periodic table, just I would like to show you once again the periodic table that we have referred yesterday. So this is a periodic table. Here we have seen the study of sixth period, that is the lanthanide elements, which are also referred as the 4F elements. After cesium, francium is there having atom number 87, after which radium atom number 88. This is 7th period, and here actinium to lawrencium, that is atom number 89 to 103, which is shown a separate list here. Here from atom number 89 to 103, all these elements are collectively called as lanthanide elements because the series is given the name as actinide, because actinium being the very first member of the series, hence the name is given as actinide series. So there are again 15 members are there from actinium to lawrencium. Here you might be looking at this series. The first 4 members, that is actinium 89, thorium 90, protactinium 91, and uranium 92. These are the first four members. They are shown by a black color, while other members from atom number 93 to atom number 103, they are shown in white color. The reason for these two colors is that the first four members, actinium, thorium, protactinium, and uranium, these are the first four members. They occur naturally. Remaining members from neptunium to lawrencium, they do not occur naturally. So these members are known as the man-made elements or artificially synthesized elements, which are obtained by bombarding uranium-238-92 nucleus by using a suitable projectile. So here host nucleus is uranium-238, and certain projectiles such as neutrons, alpha particles may be used so as a bombarding agent so as to form either of these elements. Here, the elements neptunium to lawrencium, they exhibit comparatively higher atomic masses, and hence these are the elements are also known as the SHE elements of the periodic table. The word SHE stands for the super heavy elements of the periodic table. So these elements, they do display the higher atomic masses. For example, californium having atom number 98, having highest atomic mass such as 250. So such higher atomic masses were exhibited by these elements, and hence these elements are also known as SHE or super heavy elements of the periodic table. These elements are also known as TU elements because the word Tu stands for transuranic elements. So those elements which are situated after uranium are known as the transuranic. So the elements which are situated after uranium, that is atom number 92, all these elements, all these man-made elements are known as the transuranic elements. Now, just now I have given you the reference that the elements from atom number 93 to 103, they are man-made elements. They do not occur naturally. So in the early days, when these elements were discovered, the scientists were thought of that what are the names those should be given for the newly synthesized elements, and the name should be such that that name should be universally accepted. In order to give such names, they have chosen the names of certain planets. For example, Neptune and Pluto, these are the planets. And hence, the scientists in the early days, they have given the name for these newly discovered, newly invented or newly synthesized element as a Neptunium. Then the plutonium. In the early days, the synthesis of all these elements were carried out. So again, new elements were again synthesized. The question arises that again, what the name should be given for the newly synthesized elements. And they were thought of that we have to give the name of the area where a particular element that is discovered, that is synthesized. So one element that is newly synthesized element, it is synthesized in America, and hence the name is given as americium having atom number 95. Then another element that is again invented in USA in the city Berkeley, and hence from the name of the city, the name of the element that is given as a berkelium. One element that is synthesized in California, and hence the name is given as a californium. So scientists were given the names of the planets, the name of the areas or the region where these elements were discovered. Now, again, the synthesis of all such transuranic elements or SHE elements were continued in the early days. And again, there was a big question what the name should be given for the newly synthesized elements. Again, the scientists were thought of that we have to give the names of certain Nobel laureates who have given major contribution in the chemistry of these elements or the chemical reactions. and those scientists who have received a Nobel Prize in the early days. In this regard, they have given the name of one scientist, that is, perhaps you might have heard the word Curie temperature in physical chemistry. Name of the scientist is a Curie, from which the name of curium as a SHE element is given. One element that is known as Einsteinium, having atom number 99. This name is given from the name of the scientist, that is Einstein, who have given a important equation, that is E is equal to mc square. Then you might have heard the name of the scientist Fermi gas model, from which the name fermium atomic number 100 Fm that is derived. We know that 2019, this year, was celebrated as a IYPT, that is International Year of Periodic Table. We know that Mendeleev was regarded as a father of periodic table, who made a major contribution in the charm of this periodic table. In order to give a a justice for newly synthesized element, scientists, they have given the name of the scientist, that is Mendeleev. So from this name of the scientist, who is regarded as a father of periodic table, from which the name is given as a Mendeleevium. Now, the prize that is given for major contribution in the field of chemistry, and hence the Nobel Prize that is given from this name of Nobel Prize, the name is given as a Nobelium, and Lawrencium, the name of scientist Lawrence, and hence the name was also derived from the name of the scientist, that is Lawrencium. So this Neptunium to Lawrencium, that is from atom number 93 to 103, all these elements were given the names of the planets, the names of certain areas where these elements were synthesized, and certain names of these scientists was also given. So here again, time is running up. Only 1 minute and 20 seconds are left. We are going to continue this actinide elements tomorrow also. We are going to continue some important aspects of this topic. So here I would like to conclude this session, and again we are going to start the session tomorrow also. If you are having any question, you can ask. Only less than 1 minute is left. I am going to unmute you all participants. You can go through the video also. I am going to upload the video. If you come across any difficulty, I have also open your mic. If you want to ask any question, you can ask. All your mics are open. Study well. And if you are having any